So now let's talk about boosting. So with bagging, we need unstable algorithms, which are passively generating the diversity by just training the same algorithm with different randomly sampled subset of the training set. So with boosting, we will proceed differently. We will try to actively generate new classifier from data that is difficult for, I would say, the classifiers we have so far in the process to handle. So the idea with basic boosting, which is the original boosting, is that we split the training set into three subsets, X1, X2, and X3. So they are like three data sets of the same size, 1/3 of the original training set. And then we train the first classifier H1 on X1. So basically, usual thing, we just train it as is. But then we will evaluate X2 dataset on H1, and we will just put aside all the misclassified data. And then we will add the same number of well-classified data, pick randomly. So if we have like 50 misclassified samples, we add 50 more well-classified samples from X2 according to H1, and we build what we call X2 prime. So X2 prime here is really a new dataset to train classifier H2 that is more focused on the samples misclassified by H1, not only with, but I would say the focus is stronger. And then we just look at the results from H1 and H2. So we have like H1, which is a regular classifier, H2, which is trained in a different mix of misclassified and well-classified data. And then we evaluate the X3 data set with H1 and H2. And we pick only the data where H1 and H2 are disagreeing. So basically, when there is a disagreement between H1 and H2, we use that data to put it in the X3 prime. And from that, we train classifier H3. So then we have three classifiers. And the idea is that for new test sample, we just test on H1 and H2 in parallel. If they agree, then that's that class. If they disagree, then we use H3 to solve that issue. So that improves performance, but it requires very large data set because X2, X3, and X2 prime, X3 primes can go into it can be really small. And as such, we need to have a bigger original training set to reach that point to have more samples in general. And likewise, we are separating the trainings data set in three subsets of about the same size, which means that we can get into troubles if these datasets are too small, according to the model we are using for the training. So now let's talk about adaptive boosting, which is based on the same idea, but now instead of making subsets, we are just reusing the same dataset as is. So this does not require very large datasets, even though with large datasets it may work better. And that can be used to generate an arbitrarily large number of classifiers. It's not just 10 or 25. We can go with thousands of models if we are able to deal with to do our task. So there is like the adaboost.m1 model, which we'll see here. It is just one of the different variations over adaboost. And this one is really adapting the sampling probability according to the errors of the basic classifiers. So this sampling probability is designed by PGT. Here we say P1T because we initialize to uniform weight. So all samples have the same probability of being sampled at the beginning. And then we sample a new dataset XJ from X according to probability PGT, and that is from size N. So the sampling is with replacement, but based on the probability PGT. Then we train our classifier HJ from that sampled dataset XJ, and we look at the error rate. So, and if the error rate is more than 50%, we interrupt the algorithms where the error rate, the epsilon here is defined by this equation. So basically, we are summing over all the samples. We are looking at the 0-1 loss, basically if there are mistakes, but reweighted by PGT. So basically, this weight is important that will allow to modulate the effect of the different loss, different see the misclassification from that model for data xt versus RT. That will be the 0,1 loss that we use inside the sum to evaluate the epsilon j. And then, so we interrupt. So basically, if the epsilon j is less than 50%, we just stop it here. Otherwise, we continue and we have the probability pj plus 1t, which is computed according to the classification of the dataset X by Hj. So we adjust these probabilities, increase the probabilities of hard samples, the samples that are not well classified, and we repeat it to generate L basic classifiers. So boosting and AdaBoost do not require very precise classifiers. So they can be quite rough. They can be weak, what we call weak learners. So these are algorithms with an error probability of less than 1/2. So they don't make more mistakes. So they are better than random classification, random guesses. But then it's that much better. They just need to be slightly better than 0.50%. And relatively unstable. So we want to be sure that from one case to another, they don't always bring the same kind of output. So weak learners are quite good for allowing good diversity in the classification. We can really have these different models making mistakes differently in general. And a way to build that is to rely on decision stumps. So these are weak learners commonly used with AdaBoost. So the idea is to train what was said decision tree with one level, which is a root, and the root is the decision stump directly. So it's basically a decision over like one variable. So we just say that the gamma here is the index of the feature of the variable to use. The V here is the threshold over which we are comparing the value of X at that index. And the theta here is basically the sign or the direction is like, in fact, it's equivalent to is greater than or is less than. And mathematically speaking, we can express it that way. So basically, we are sorting all the samples in increasing values. So we just kind of reorder them in terms of their values, and that independently for each variables. And then we just compute the thresholds, which are basically in between. So if we see we have like this x, this x, this x, this x, so x1, x2, x3, x4, with a small tilde, we can see that the threshold is really the values in between at 50-50. So we have one threshold here, one threshold there, one threshold there. So we built this n-1 thresholds over the sorted n samples. And these thresholds are important because they will be used after that for making a decision. So they are like candidate values. And what we do, we build the Hj, which is basically the set of possible thresholds and I would say sign and index according to the variables. So this is equivalent to d times n-1 times 2 values that are put in the ensemble Aj. And then we have the big set A that is just unifying everything. And then from that, what we do is that we look over, we have an enumeration of all thresholds, variable index, and sign, greater or less. And we just look at the configuration in these triplets, in all the triplets, that is minimizing the error on the training set. So from that, we just go on with the kind of value we've got, kind of outcome. So basically, if we look at the ensemble training error with AdaBoost, we see that it will kind of go down with the decision terms over time, but it is asymptotic. Likewise, for the test error, it's kind of following the ensemble training error. But the thing to look at is the fact that the individual weak classifiers are increasing in terms of error because they are trained more and more on the hard samples. So that makes sense. We just kind of increase the sampling weight for the hard samples. So more frequent, and that will just make the error higher because we weight more these samples in the computation. So Adabos looks like that. So we are initializing the probabilities for each data, P1T. Usually it's uniform to begin with, and then we adjust it. And then for each classifier of our ensemble, we will sample the dataset XJ from X according to the probabilities PGT. We will train the classifier from the dataset. We will then calculate the error weighted by PGT on all the dataset of our training set. And then if the error is more than 0.5, we should stop. We should go back at the last iteration and say, that's enough. We cannot continue because the current classifier is worse than bad luck. It's worse than chance. So, and then we will calculate the beta J, which is coming from the epsilon J. And this is a result that is used the beta here. It is later used to adjust the Q that is in fact the value that we will just renormalize to get a probability. So that setting is allowing us to adjust, increase the probability of misclassified samples and decrease the probabilities of other well-classified samples. And in the end, once we have a model that is trained, we will evaluate the classification of a data that way. So we have the ensemble decision, and we are making a weighted vote, basically, but the weight is log 1 over beta J. So that depends on this beta. That is the weight we use for making our decision. So it looks that way. So basically, we are building a 2D set of about 10 decision stumps make with Adabos. So we have this case here where we start with one threshold around -1 for x1. This gave us the first split, and then the second split is again over x1, but for about 1. So we're looking that is less or more than -1, less or more than 1. And then we have in the third iteration, we have another split that is now a little less than 0 for x2, and so on. So we see here the construction over the iteration of the model. And then we can see that it leads to relatively fancy setting, but still able to separate the different sample correctly. So somehow Adabos is maximizing the margins for the classification. So the point here is that we are looking at the votes from each individual members. And as such, we can see that we are trying to maximize this classification, these margins, by focusing on the difficult data. And the difficult data are usually the data close to the decision boundaries, frontiers. So these are the data in the margin. And as such, we are making use of a weighted vote because the H bar is a weighted vote. And then we just compare the for and the against class for this. And then for many classifiers, we can get a good decision. Otherwise, so if we are in the class, the H bar should tend to 1, and if we are in the other class, against class, which it would go to -1. So wider margin lead to better generalization. And there are many variants of boosting, and LP boost is in fact a case that is using linear programming. And that is somehow the idea that at each generation, we relearn the alpha for all current classifiers, and that is really close to SVM on many aspects. So there's just a connection between Adabos and SVMs that are, I would say, some connection. SVM is more with the geometric margin, while Adabos is more with the voting margins.